Hello everyone, welcome back to my channel, Black Box Engineering. I am going to be continuing my technical series here on the circuit design I made. Last video I talked about active filters and brought up a little bit about bandpass filters. Today I'm going to be talking about pretty much the last step before actually showing you the circuit design I made to actually build something physical to use this whole mathematical concept, the frequency filter stuff, so on audio. So anyway, I'm gonna switch over to my screen here, and you saw some of this in the last video, just kind of a sneak peek here. So let me just switch to my desktop here. Just as a recap, oops, I always forget I gotta click things. So this portion is the high pass filter. This portion is the low pass filter. And then, like I said before, these are the unity gain buffers. So I'm gonna show you what happens if we don't have these between stages here. I think it'll be a little bit easier if I remove this one first, between the voltage divider and the output of the high pass filter. So this particular setup is blocking, it's starting at, what did I say? I put a 5,000 hertz on the high pass side, and then the low pass side over here I have set to 25,000 hertz or 25 kilohertz. So let's remove these stages. Sorry, I misspoke. I'm going to remove this and show you what it looks like without it. I'm going to delete it because we need to have valid circuitry here. It might actually work fine, but we'll find out if it actually stays stable or not. So it was 31.83 nanofarads. And then the higher value is going to be the 6.4 or 6.37. I'll include decimal places. 6.37 nano. Copy. Paste. Paste. I'm gonna move this. I don't like it when things overlap. There we go. I wanted the split window thing. So if I measure this output, it does look approximately correct. I actually want this to be closer to 9.5K, because that's going to bring us to the very, very close to the expected input level. It's actually a little bit lower than what I had earlier, because I don't have the unity gain buffer at the end here, so that might be affecting it a little bit here. So it might be losing some voltage in the whole thing. But so this does seem to be working relatively correctly. If I bring, actually, one thing, I gotta change this. Let's do 2,000 points, and we need the start frequency to be 1,000 hertz. Well, let's say, I don't know, 30K. I'm gonna reduce. Oh, not 1,000K. That would be wrong. All right, so let's just zoom into this spot here. We're going to measure at the 5,000 hertz level, and then measure at the 25K level. Get as close as I can. So you notice that the difference here is in the same like horizontal space. It's pretty much identical across the line, and that's kind of what we're aiming for. We want the cutoffs to be at the roughly the same point, because then we know it's performing better. Also, like I said before, the non-attenuated part is going to be a lot more flat compared to the full inactive bandpass filter, like I described before. So clearly the voltage divider doesn't really affect this too much. So if I add it back in, I'm gonna copy and paste here. If I add this back in, let's see if it does anything to the signal here. Okay, so it definitely brought it way closer to the approximately 13 decibel level, at least between the cutoff regions. 13.5 and the reference is 13.9, so minimal losses here with the added voltage divider. So it did keep the integrity of the voltage. It's probably because the output impedance is not much different than the input impedance on the Sorry, I had to speak a little bit more clearly. The output impedance of this filter is going into the input impedance of this side, which is technically our full output. I hope that made sense. It's a little hard to wrap your mind around that whole thing there. But realistically speaking, this output impedance right here is going to be, it looks like it's very similar to the input impedance of this particular set of resistors. So it's probably why it doesn't really matter that much that if this particular unity gain is here or not. Technically it did help a little bit, but so I'm going to remove the first stage one, and we're going to see a much different change here. So let's close this, go back to full screen and zoom in. I'm going to cut this part. I'm going to just add a simple wire. I'm going to leave the output one just to see what happens. And if I measure the output, and I don't want the phase stuff, let's change this to logarithmic and compare it to the, let's see if the cutoff range is where we want it to be. So if I bring this to 5, and then we need a second cursor, bring that to 25 kilo. Okay, so here's where it definitely matters. Before we had these spots kind of at the same level, so it definitely changed it. It's less if it's not attenuating quite at the right spot. So I wonder if removing both sides is actually gonna both unity gains is gonna be detrimental to the application here. So let me just do that real quick. Okay. Sorry, this does take a little bit of setting up to get right. Wait, what am I measuring? Oh, I didn't measure the right spot. It's attenuating it a little bit, and let's see if the cutoff is as expected. $25. Okay, so I'm going to bring this in the window here. This is at pretty much 5,000 hertz, and this is 25,000 hertz. You can see that the difference now is pretty much 2 decibels. That's pretty significant when we're talking about a filter here. If I add those back in, it's gonna make the performance ideal, or as ideal as we can make it. Basically, it's not ever gonna be perfect, but so I'm just gonna add them back in. And again, this is just kind of an exercise to show you why the unity gain matters. It probably matters more for higher frequencies, honestly, rather than lower frequencies. Things start behaving weird at high frequencies. So if I had to do an educated guess there. Okay, so that one's back in. And then add this into the mixture. Okay, I'm going to rerun this. Put this on logarithmic scale. Don't plot the phase because I don't need to see it. And remember, we're comparing to the baseline of an input of that flat AC signal at 1 amplitude and frequency. Well, it's changing frequency. It's just staying flat because there's no filters on the input, just the input side. So if let's just zoom in like we did before. Let's see what the decibel difference is now. So marker at 5 kilo. Marker 2 at pretty much 25 kilo. The difference is like 0.1 decibels. Way better. This is as ideal as you could possibly get it with an active bandpass filter, at least with this third order Butterworth filter. So that's kind of why you need the unity gain buffers between stages. Technically, I guess the idea behind it, because there's a mismatch of this impedance and then this impedance, you're actually technically incorporating standing waves. So some of that power is not being fully sent to the output. Some of it's being reflected back into the system, and that's why you see losses and imperfect cutoff frequencies too. So this kind of like I said, it bridges the gap between high and low impedance. Typically, the input impedance of an operational amplifier is much lower than the output. So, yeah, this is the full thing that I really based my entire design off of. Is this Butterworth filter with unity gain buffers, and then I'm gonna be getting into the post that I made here. So thanks for watching. Like, comment, subscribe.